continue our discussion of Dirichlet distributions and the connection to LDA and other good stuff like that. And so I feel like it might be useful to do a quick review of what we saw last time, because I think that material was somewhat, shall we say, dense. So let's try to go back and sort of think about again what we'd like to do. So what I want to do is again revisit the idea of a Dirichlet distribution itself as a distribution over distributions, right? Which is the first point where it starts getting a little bit crazy. And just go back over that again, and then we can immediately go into LDA, latent Dirichlet allocation, which is a way of doing clustering using Dirichlet distributions. And we'll try to see how it generalizes the idea of using mixture of Gaussians. You can think of it as a sort of mixture of Gaussians on steroids, but there are a lot of steroids. So, and then we'll talk about. I had promised that LDA would be your sort of way of doing clustering without needing to know K, and I kind of lied a little bit, and I'll tell you how I lied and how to fix that lie. All right, so I'll go through this a little bit more quickly because we did see it once before, but I want to make sure we sort of follow what's going on. So we talked about mixture models, right, as a way of doing clustering. Right, so you have, let's say, a mixture model. Right, and the mixture model idea is that rather than just, in a lot of the other clustering problems where you just say, okay, I want to group things into clusters and minimize some cost, here you posit some generative process. Right? So there's some generative process that generates points, and it's described by some kind of mixture of distributions. So in particular, you have, let's say, K clusters. Right? And you have first of all, some description of what size each cluster has. And of course, we're talking about distributions, we're not talking about size so much as probability. So there's some set of probabilities, pi 1 to pi k, sigma pi I equal to 1, that describe the relative weights of each cluster. Right? So maybe one cluster is big and has half the mass, and there are two clusters that have 1/4 of the mass. And that's the pi 1, pi 2, pi 3. Right? But of course, that's not enough, right? Just knowing that I'm likely to be in this cluster with probability half doesn't tell me what this cluster actually looks like. So what you need is some actual information saying for each cluster, there is some kind of distribution that describes things in that cluster. Right? So in the easy case of mixtures of Gaussians, there was one Gaussian for each cluster. Right? And so we said that the probability of seeing a particular point, right, given phi and pi, was to be viewed in the following way: that you first choose which cluster you're going to be in, and once you do that, you now use the distribution associated with that cluster to decide what your point is going to be. Right? So essentially, this would look something like this. It would be sigma pi I, probability of x given phi. Which is like saying first pick a cluster with a certain probability, and then pick a point in the cluster distribution associated with that cluster. Right? And what we said was that you can reformulate this, we'll call this distribution G, as sigma pi I delta phi I. And the way to think about this operation was to think of that you are generating, so this is going from I equal to 1 to k. You are generating this distribution, you can think of as a bunch of spikes. And the reason I want to say this is that rather than just reasoning about distributions over the reals, I want to be able to talk about distributions over distributions. So the first step in doing that is to express what are my sampling distribution P in terms of entities that are distributions themselves. So this quantity here is basically, think of it as a spike. So think of the space of all distributions, phi I. And then there's one spike at phi 1, there's one spike at phi 2, and there's one spike at phi 3. Right? And again, if you were just sampling from 3 points, if I had the numbers 1 to n, I could think of it as having delta functions in each of them. And that would be like a normal point, like a die, throw a die 1 through 6. You have a delta function in each value, discrete value. And so you're doing that. Similarly, you can do that here with a delta function, which is the equivalent of that discrete value, but of course now you don't have to do this. So this for reformulation is just that. It's a reformulation of what we were doing before, but changing the underlying space we're working with to be a space of distributions. And that's going to be important for the Dirichlet calculus. Well, that's so far so good. I mean, I know this caused some confusion, but I just want to emphasize that this is not saying anything different to this. It's just saying it in a different way. Okay? Okay. The trick now is that G is a fixed distribution. You have phi i's and pi i's that are fixed. If you now say, choose the pi I from some distribution, right? Some unknown distribution, then G itself becomes a random thing, object itself, right? Because for every, you can think of, okay, with some probability I choose some set of pi i's, that gives me one distribution. With some probability I choose a different set of pi i's, that gives me a different distribution. So in effect, by rewriting that sampling distribution in this form and allowing these to be random, I can now generate random distributions, which is the thing I wanted to do, and that's why I wrote this out like this in the first place.
G is a random variable here then.
It's a random variable, but the variable is defined over the space of
the
distributions now, rather than the space of like atoms. And that's the extra sort of the categorical lifting we're doing one level up. Right? We're reasoning about distributions over distributions, and that's what happens by allowing this to float. Okay. And that's going to be important for what happens next. Because you need to have that ability to say those things, to have that language. And that's what we're building up here, the language that allows you to say these things. Okay?
Sorry.
Yeah.
Is pi I a weight?
You could, yes, pi I is intended to be the weight of a cluster. But now I'm saying even those weights can be chosen randomly from some distribution. Right? Okay. And that's the key. How do we choose pi I from a distribution? What does that even mean? For that, we need to think of pi I somewhat differently. Instead of thinking of pi I as a bunch of numbers, we think of pi I as a point on the simplex. Right? Remember the simplex, the sort of delta k minus 1 is equal to the set of all pi 1 up to pi k. I put the k minus 1 because I'm going to put one constraint on them. So it's actually a k minus 1 dimensional space. And that's exactly the space we want to sample from. We want to sample from this space because any point in this space is now can be reinterpreted as a distribution. In particular as a multinomial. Okay? Yeah? And then once we do that, we can now say, okay, let's define a distribution over these that we can sample from, and that is the Dirichlet distribution. So the Dirichlet distribution, right, with parameter alpha, and let's say its parameters alpha 1 up to alpha k in general.
There can be many such pi's, right? In delta k minus 1 set.
It's an infinite set.
Yeah. So
Exactly.
you have written up to k. So it's confusing. Written up to k, pi 1 to pi k.
Well, it's k.
It
Yeah, it's k dimensional. You're saying you could have more than k. I mean,
the pi is the point, right? In the simplex.
pi 1 through pi k is the point.
Pi is a vector. I would say pi 1 is a vector.
It's a tuple. It's not a vector.
Tuple.
A vector means I can add them, and a vector means it satisfies vector properties. These things on the simplex don't satisfy vector properties.
Okay, so
I can't add 2 points on the simplex and get another point on the simplex. Right?
Okay.
If I add this point and this point, I get that point there. So it's not a vector, it's a tuple. But I'm being pedantic. So go on.
So I was thinking like pi 1 is kind of a fixed dimensional vector. So all
Pi 1
pi's
through
are
pi k is a fixed dimensional object, yes.
Okay.
Pi 1 is just a coordinate. It's a number. Pi 1 is a number, pi 2 is a number. That's why I can write that. Right? You can think of this as the probability of the mass of the cluster 1, the mass of cluster k.
Okay.
That's the intention of these things. Right?
Oh, I got it.
Right? So pi 1 is half. Pi 2 is
This is a
1/4.
combined pi basically,
Yeah.
right?
Pi is the whole thing, yeah.
That's what I can
Yeah,
feel. Okay.
yeah. Okay. Good. And so, like I said, you can write this out now. Anyone remember this distribution? So, what I want to say is that if I draw a sample from this distribution, I'll tell you what the probability of a particular distribution is going to be. So, the probability of a particular pi, given alpha, is going to be some large normalizing constant times what? Anyone remember this?
The gammas, I think it's some gammas.
Yeah, the gammas are the normalizing constants, but I'm ignoring them for now.
Pi
'cause
to
I
the
hate
power
numbers.
alpha minus 1 something.
Sorry?
Pi to the power alpha minus 1 something.
That's right. And again, it's not something that you should remember, but it just, I'll just write it on here.
Something like that.
Okay? In other words, in some sense, I have told you now what this distribution means by telling you what it means for a point, you know, what is the probability of any particular point in the simplex according to this distribution. That's how we define distribution. So now we're saying this, if I give you these set of parameters that describes the distribution of the simplex such that the probability of any point on the simplex is this quantity here, normalized appropriately. And we talked about some nice properties of this, that we said that, okay, let's first pretend that all the alpha I is equal to some fixed alpha, right? And then what did we say? We said that if you set, let's see, if alpha is something, you know, greater than or equal to 1, right? As alpha increases, you get more and more concentration around some center point. And in particular, that center point is whatever this is. So in this case, when all the alphas are the same, the center point is the normalized center of the simplex. And as the magnitude of alpha increases, this concentration gets more and more. So it gets sharper and sharper and sharper. Remember we talked about that. And you can prove that by showing that this quantity is maximized at the center, so it's also in the mode. You can also show it's the mean. And that because of these alphas getting bigger, it drops off very rapidly as you go away from it. So hopefully you all remember this from last time. Right? So in other words, you can think of, if you look at the Dirichlet distribution with parameters alpha I, the sum of the alpha I is like a concentration parameter. Okay? The equivalent of a variance or a 1 over variance. Okay? And the vector alpha 1 up to alpha k divided by sum of alpha I, which is normalized and therefore is also a point of the simplex, is like, I'm going to put in quotes, a mean. Okay? That's one way to interpret what's going on in this. That makes sense? And the point of this whole exercise again is to allow you to discuss distributions over the simplex, because now if I want to say what is G, I can say, okay, I'm going to sample a point from here, from the simplex, according to this Dirichlet distribution with parameter alpha, and let's assume alpha is fixed. So in most of what we talk about, alpha will be a single fixed number. Okay. So the mean is at the center. And that will give me something to plug in here, which will give me a distribution. So that allows me to sort of reason more generally about these parameter choices. Okay, so before we go on, are there any questions about this? And again, the main takeaway you should take away from this is that the Dirichlet distribution allows you to build probability distribution over multinomials. Each of these points represents a multinomial, a discrete distribution, over k atoms. And allows you to reason about this thing. Yes?
So multinomial distribution is different, or Dirichlet distribution?
What is a multinomial distribution? What's a binomial distribution?
So binomial distribution is like you trials. I mean, there are a few trials, like you toss the coins.
What's the parameter of a binomial?
Yes or no, yes, no.
Yes, P or 1.
P or minus P, right? So a binomial distribution says I have a parameter P. So if a binomial, I have a parameter P. And then what this means is that I see, I see the atom number 1 with probability P, and I see atom number 2 with probability 1 minus 1.
Multinomial is like multiversion.
Okay. So I should write this as P and Q, where P plus Q is equal to 1. So that's exactly.
Yes. So why don't we sample from multinomial distribution? Why are we going after all this?
Why don't you sample from a multinomial? What do you want to sample from the multinomial?
A point, basically, yeah.
What do you want to
pi 1, pi 2, pi 3, all those things.
Yes, but, okay, the pi 1, pi 2, pi 3 is a multinomial distribution. You will sample from it to do the clustering.
Okay.
But what are the pi's in the first place? It's like saying, okay, I can sample from this to decide, from this multinomial, to decide which cluster my point should belong to.
Okay.
But how did I know these weights, half, 1/4, 1/4? Where did they come from?
They are coming from multinomial.
But how? Or why did I choose half, 1/4, 1/4? That doesn't come.
Probability
That
distribution.
Sorry.
It's a probability distribution.
But where did it come from? If you were trying to be,
I mean,
I won't say Bayesian, but if you want to sort of be principled about where these numbers come from, they're arbitrary numbers. How did I pull these numbers out of a hat? Why not 1/3,
Yes.
1/3, 1/3? Why not 1/4, 1/6, and whatever the difference is?
yes.
how do I decide which one is the right one? The argument here is that the principled way to do this is to say that there's some distribution over these choices. So I first pick one set of such choices and use that as the model of my cluster. And that's what the Dirichlet distribution is.
So I can use any such fractions which are summing to 1. Yes. Okay.
So a sample from a multinomial is an integer.
Okay.
A sample from a Dirichlet is a multinomial.
Okay. Say again this thing. A sample from?
A sample from a multinomial is a number,
Yes.
like 1, 2, 3, 4, 5.
Okay.
A sample from a Dirichlet is a multinomial.
Okay.
That's why you would sample from the Dirichlet to get the multinomial, and sample from the multinomial to get the integer.
Okay.
That's why I think is most confusing about this, that you have to kind of do that extra level of reasoning about this.
There's no other distribution other than Dirichlet that can help us solve this problem?
There are.
There are.
So there are others, yeah. The Dirichlet is closely associated with the multinomial.
Okay.
If you have things like Gaussian processes that give you sort of Gaussians and stuff, so there are other ways of doing this.
Okay.
Yeah. So there's a way to, essentially the way you, there's this called number of consistency, I don't quite understand. But basically the idea is that what you want to build, you can posit some existence of an infinite sort of distribution over distributions with the property that over any finite subset it looks like one of the things you want it to look like.
Okay.
And so you can construct other subsets. There is something called the Pittman-Yor process, and there's other various processes that give you other things. There's a whole nice sort of theory of non-parametric spaces that gets you into all this. So this is just one class. But it's easy because multinomials are the most, in some sense, the most basic distribution you can work with. And for LDA in particular, that's all you need, as it turns out. You don't need anything more fancy. You had a question?
Yeah, I just wanted to say, you can define your own distribution to sample multinomial.
Yeah.
The cool thing about Dirichlet is those hyperparameters, alphas, that are sort of nicely defined how you sample them.
Yeah, I mean, and again, this is because I'm not really steeped in the tradition. I always think of hyperparameters as turtles, right? I mean, in other words, there's one turtle, and there's another one below it, there's another one below it. I mean, there's nothing to stop me from putting a hyperparameter on these two, right? I mean, at some level, you have to argue, okay, that this is the right set of hyperparameters to work with. And one argument you can make for why this is natural is that it's boiling down to a location scale principle. You're just saying, okay, there is some location, the mean, and there is some scale, your variance, and that's all you need to describe this entire family. You're not asking for too much. Whereas here, I'm asking for many, many parameters, right, in order to do this, and they're kind of more low-level parameters. So there's a sense in which you, and you could, there's no reason to stop here. You could build, more and more hyperparameters over these things. But how you decide when it's okay is again, something that is a matter of taste and to some extent modeling. So these are good, but I would keep that in mind, that this is also a choice to make to stop here at one level up and not going higher.
I have one question.
Yeah.
Just in terms of practical concerns.
Yeah.
So let's say many things in the data, in the real world data, is power law, right?
Yeah.
So which sort of indicates that we would like a multinomial, it would be sort of like power law.
Yeah. Yeah.
That would have probabilities that follow sort of the power.
Sure.
Is there a way to configure those?
That's a very good question.
Because it's isotropic, right? I mean, it's concentric, isn't it?
So, yeah, this is concentric. Well, if you fix this, it's concentric.
Yeah, okay.
I don't know. This is where this gets sort of out of scope of what I can cover or what I even know in a clustering class. I think it's something where you need to take a class on non-parametric statistics to be able to answer questions like that. In other words, I need to take the class to answer your question because I don't know the answer. It's a good question though, and I think there probably, my guess is there must be a way to do this. I just don't know what it is.
Let's say that those clusters would be some kind of topics, right?
Yeah, no, I completely agree with what you're saying. It makes perfect sense that you want to build a model more. Of course, to be fair, right? I mean, you can get a power law decay here. It's going to be one of these points, right? The question you're asking is, can you make sure those points have sort of higher probability than the points that are more even?
Because the points are like, they jump all
Yeah, so what you're basically saying is that you want to give more emphasis, roughly.
They're not local.
No, you're going to want to give more emphasis to things kind of here. Right? Because the falling off means that you're going to prefer one dimension much more than the other and so on, recursively down. So you want things that are coming out of the corners. One thing I do know which I will make a half-assed attempt to answer your question at, is that if you set these parameters to be very small, so these are negative, you get this kind of effect. So if the alphas are, let's see, less than 1, okay,
Oh, really?
then this reverses concentration. It starts growing from the boundaries. And that might be a way to go over this. Whether it actually happens that way, I don't know. But intuitively, you know, this is basically going to the denominator. You're getting this 1 over poly and 1 minus alpha. Maybe that does. So maybe negative values of alpha are what you need here for this to make sense. Yeah?
Thank you.
So it's a good question. I don't know. Okay. All right. So this is some sense is, you know, I did want to talk, and we'll see how much time I have to do that, about Dirichlet processes. Because, okay, let me back up a second. In one sense, you might argue that I've not done anything that interesting yet. I mean, yes, I've given you a way to choose the pi i's at random. Okay, fine. I'm not. What would be really interesting is that I could let this go off to infinity for some sense, have an arbitrary number of clusters, not to pick one. And there is a way to do that with this thing called the Dirichlet process, which I do want to mention at some point today. However, to study the basic sort of LDA concept, which, you know, I think is an interesting way of thinking about clustering, especially for documents, you don't need yet anything more than just this. So what I'd like to do now is go from this into how we do latent Dirichlet allocation for documents and words and text, at least a little bit of it, and then point out how, you know, you now need to start changing things if you want to allow this to be truly non-parametric. Okay? And hopefully the process of doing the LDA, this example, will show you why these get used and how useful they are. What I'm not going to do is cover the inference process for these things. Those are very hairy. And again, Tom's class is kind of a class that really covers in detail how to do the appropriate sampling variational methods for these kinds of things. So I'll just write down the function that we want to optimize and leave the rest for later. So, not later, for someone else. So, okay. So this was, you know, this created a big splash, and I think is still probably one of the best known methods for doing what is called topic model. So it's a specific example of a specific kind of clustering problem, which looks like the following. The problem you want to solve is that I have a document with text in it, and I want to discern what the document is about. In the language of clustering, you could say, I want to put this document into a cluster. What it is about is a topic. So there are usually K topics, and I chose K deliberately because topics you can think of as clusters. Okay? And you believe the document belongs to some number of these topics. The document may not be about one topic, it might be about multiple things. So it has some partial membership in each of these topic classes. So a point has some partial membership in these clusters. Right, so in this case, so just building up this parallel document, sort of within quotes, it's kind of like a point, and a topic is kind of like a cluster. Okay, and the LDA method is a generative model that attempts to solve this problem. In other words, it posits a way in which such a document or collection of documents might be created. And then it describes how you might go about trying to discern the parameters and so on. Okay. So in order to describe the Dirichlet allocation algorithm, what I need to do for you is tell you how it views the generative process and write down the entire probability function. And then, as with most things in probabilistic models, you just throw a hammer there. So see, okay, how do I estimate these parameters from the data? Okay, but the model, the generative model is what's important. So remember that in our mixture of Gaussians, we said, you know, select a point from a topic, and then select a topic first, and then generate a point from that topic. Right? That's how we thought about generating points on the Gaussian. That's kind of what we want to do here. So imagine that we have a series of documents. So we're going to have documents D1 up to D, let's say D, or let's say capital D. Okay. These are documents that are being generated by some process. There are key topics. So there's topics, you know, T1 through TK. And there's a vocabulary of words, the words being used in all these documents. Right? Maybe all these documents are from a newspaper corpus of some kind. So there's some vocabulary. You can think of the union of all the words that you see. Right? So there's some words W1 up to WB. Okay? How am I imagining the process by which a document is generated? So the idea is this. So first of all, we're going to think of a topic as a distribution over words. Right? In other words, when you think of a topic, like say, I don't know, cricket, right, or football, or some sports topic, there are certain words that will keep showing up. Right? You might talk of a first down. You might talk of an offside penalty. You might talk of certain things. You talk about American football. If you're talking about cricket, you might talk about other terms. So there are specific terms you expect to see, and some terms will occur more often than others. So it is reasonable to say that a topic is some kind of distribution over words. Again, in a loose analogy, a particular cluster is some kind of distribution over the space. Right? It has a certain shape to it. So each topic has a certain shape to it. Okay? We also will posit that a document itself is a distribution over topics. Right? Where to construct a document, and again, I think maybe my analogy is not quite right. The document should be a point set, not a point set. That you can think of saying that, okay, I have some particular document containing a bunch of words. This document is about, the sort of the financial arrangements the NFL has with the government. So there's football words in there, there's financial words in there, there's some politics words in there. It's a distribution over these three topics. Depending on the particular focus of the document, you might have different, importance for these different words. So different topics, but it's some kind of distribution over topics. Once you buy that, now I can talk about the process of generating an actual document. Right? So what I'm going to do is I'm going to say, okay, so for each to generate a document, right? First, pick some distribution over topics. Okay? And now let's say that each document is of size n, it has n words in it. Okay? And then to generate a word, what you do first is pick a topic from the distribution you gen for that document, right? And then each topic is a distribution of the words. Pick a word. Of course, no one actually writes documents this way. That's not the point. But this, is proposed as a model for how you might imagine a document being generated, right? Of course, these things are not independent. I'm not going to just sort of very schizophrenically pick one word from this document or that, but modulo those concerns, this may be a good way to do this. So does this generative model make sense to you? Again, I've not put any parameters on, but at least at this level, hopefully it's clear to you, how you might think of a document being formed. Yeah.
This generative model is like how the mind of the writer was operating.
I don't think anyone would claim that.
But it's like a naive representation of how
it's very, very, very naive. Yeah, because there's so much independence, right, between choices of words. Every word choice is independent, right?
Okay.
So yeah, I don't think the authors would claim this is how the writer is doing it, but they're saying this is sufficient.
Okay.
Just like with naive Bayes, like things are sufficient in order to capture what's happening. And you can make these things more sophisticated. There's been a lot of work since the really work on giving more correlations and stuff. Okay, so does this so far make sense? Yeah. In terms of, okay. So now what we have to do is make this more concrete, right? And now you might start seeing where this machinery we've built up might come in handy. So we've said that a topic is a distribution over words, and we said that the document is a distribution over topics. And we don't want to be arbitrary with these things. We want to be a little bit more concrete. What I want to do is, so if I want to be more precise now, how am I going to do this? So what I'm going to do is the following. I want to pick a topic to be a distribution over words. What do you think I should do? Given what we know so far, what might be the way to go about doing this? So I mean, a distribution of words means for each word in the vocabulary, so there's a vector of length v, I need some probability. Okay, this word occurs with this probability, this word occurs with this probability. What should I do? What kind of distribution is that? A distribution where yeah, this word occurs with this probability, this one, what is this called?
Multinomial.
Sorry? Yes?
Multinomial.
It's a multinomial. So how do I pick it? What should I do? How do I come up with a non-arbitrary way of picking a multinomial to describe a topic?
You mean random?
Sorry?
Dirichlet allocation.
Yes?
Nice.
No.
Do you mean random?
Maybe. Sure.
Then you can use the Dirichlet distribution.
We should use it. So we've said that a topic is a distribution over words. We agree that it's a multinomial because you're saying for each word there's some fixed probability, it's a discrete distribution. And now we're saying, well, how do we pick this? Well, we don't know how to pick it, so let's pick it randomly. How do we pick a multinomial randomly?
Dirichlet distribution.
So we'll fix some parameter, eta, some scalar, okay? And we'll say that for topics 1 to k, okay? Make sure I have my notation. We'll say that beta I is the distribution over words for topic I. I have to construct that distribution. So I will draw it as a sample from a Dirichlet distribution with parameter n. I will draw all the distributions in the same way. So they're all drawn from the same Dirichlet distribution with parameter eta. Okay? But of course they're going to be different points on the simplex. Right? So if you think of this as so what's happening is that I have this v-dimensional simplex, or v minus 1 dimensional simplex. Okay? And I'm picking topic 1, topic 2, topic 3, topic 4. Each of these points, if I pretended my vocabulary had 3 words in it, right? Let's say I was doing rock, paper, scissors. Okay, so this is basically, this is going to say, I don't know, let's say this is rock, this is paper, this is scissors. So my topic 1 is going to be, let's see, half rock, 1/4 paper, 1/4 scissors. That's my first topic. My second topic, which is up there, is going to be 1/4 rock, maybe half paper, and 1/4 scissors. And then my third topic, again, so on. Right? Because each of these topics is now being picked as a point on the v minus 1 dimensional simplex. So there'll be some gigantic set of probabilities over the vocabulary. That make sense? Okay, so I got that first. Now what? Each document is a distribution over topics. So to generate the document di, it's a distribution over topics. Well, a distribution over topics is a multinomial over topics. How do I pick such a multinomial over topics? There's another Dirichlet distribution. So now fix a different parameter, we'll call it alpha. And we now sample the ith document as a Dirichlet distribution over alpha. I'll put a k here just to make sure you realize it's over k, and this is over v. Okay? So now I have two things. For each topic, I have a distribution over words. And for this particular document, I have a distribution over topics. But the document is empty. Right? It's completely empty. So now what do I do? So let me actually define this as theta I is a parameter for a particular document. Yes? Yeah. And now I have to generate the words of the document. So how do I do that? Well, first I have to decide which topic that word is going to be drawn from. Right? So now I generate, so for let's say I'm in document I. So zi, so for the jth word, Zij is going to be sampled, right, from the multinomial with parameters theta I. Okay, why? Remember, theta I was the distribution over topics for that document. I got to pick one of those topics, so I'm going to pick it. Okay. Now this is a topic, right?
Can
Yeah.
you explain this thing once more? After
Okay, good.
this document.
Yeah, okay. So, for each document, I have chosen a parameter, a vector of parameters theta I, which is really k numbers, right? Which is a point on the k minus 1 dimensional simplex, which describes the relative fraction of the topics inside that document. Correct?
Yes.
Okay. Now I have to generate a word. Well, I know what the fraction of topics is.
Yes.
So now think about clustering, right? So I first pick which topic my word should come from.
Okay.
That's how that's by definition is what I do.
Yes.
These are generation parameters from multinomial. And now I have to do something next. Does the first time make sense? So what should I do? What do you think I should do next? I now have a topic. What should I do?
Once you have a topic, you know how the words are distributed.
So what should I? So what am I sampling now?
You're just sampling a word from that topic.
So I'm sampling a word, Wij, sampled from
Multinomial,
a multinomial of what?
Zij.
No. Zij is an actual topic index.
Oh, you mean it's B?
Exactly.
Zij.
That's right. It'll be beta of Zij. Again, don't get faked out by the indices, or rather, I tend to get faked out by the indices, but don't get faked out by things. So first, this basically means sample a topic, and this means sample word from that topic.
Is beta?
Notice, by the way, that the topics were constructed ahead of time. It's not like when the next document comes along, I change my topic distributions. The topics are fixed, which is why we expect there to be some structure, right? Like we expect that, in the universe, if you're talking about football, there are certain words you're going to use in certain proportions. That's not going to change from this document to the next. So this is done first. Then you do this for the document and other stuff. So now you see where the Dirichlet distribution is coming into play here. It's allowing us to sort of reason at a hyper level about what distributions we want for it to construct an actual document with an actual topics. Starting to fix this. So that's why I said it's like learning a mixture of Gaussians on steroids, right? So instead of having fixed Gaussians, you're now saying, well, I don't know what my distribution, maybe a Gaussian, maybe not. So it's something much more general. So an arbitrary fixed dimensional distribution of the simplex. Okay? So now you can ask yourself, what are the parameters of, first of all, what are the hyperparameters of the system? The hyperparameters are things you usually fix. Okay? Things that sort of the top level knobs that control the entire system. What are the hyperparameters of the system?
Of Dirichlet, V of Dirichlet, K. And K.
Yeah, so these two numbers.
Yes.
Yeah. So the hyperparameters are this and this
And K.
and K. Good.
Maybe you don't consider it as a hyperparameter.
You're right, but in this particular case, it has to be.
It's kind of.
Yeah, in this case, it has to be. If you want to get rid of it, you have to do more work. But yeah, for now, it's a. Okay. These are the hyperparameters, and these are things you have to fix ahead of time. Okay. What are the parameters of the system? The parameters actually generate the system. Well, it's all the beta i's, right? Which is basically a matrix, right? Because each beta I is a v-dimensional vector, right? Or v-dimensional tuple, since I schooled you saying that I shouldn't say that myself. Tuple, and it has and the k of them, so it's a k cross v matrix. There are also theta I, which are the parameters for the documents, and there's also the ZIGs. which are the topic parameters. And the actual data you have, what's the data you have? If I, of course, in any actual LDA problem, I'm giving you some documents. I'm saying, okay, cluster them, right? So what's my data in this notation? What is the other thing I actually have?
Words.
And words. Right? And the goal of LDA is to take the hyperparameters and the data and recover the parameters. Again, going back to the mixture of Gaussians, our hyperparameter was K. Our other hyperparameter nominally was, these are all Gaussians. It's not really a formal parameter, but that's essentially what our implicit parameter was. So given K, these are all Gaussians, and the data, we had to recover the mixture model and the actual parameters, the mean, the variance of the Gaussians. Similarly here, given the hyperparameters, K and the description of the space of distribution we're working with, and the data, you want to recover the partition function. So in particular, you want to know how a document is broken down over topics, how a topic is broken down over words, and what the topic of any word is. So you're actually getting a lot of information from this. When you look at results of using LDA, you can actually color individual words in a document with what topic they have. You can do things like what are the similarity between two topics, but you can look at these two vectors for two different topics and see how close they are to each other. You can do all kinds of fun things like that. So you're getting a lot of information from this process if you can learn these parameters. Okay. And in particular, what you're trying to learn is the following. So again, there's a nice graphical model way to write this, and if I knew graphical models, I would write them down to you, but I don't. So I'll give you some pointers. So
There are 2 boxes, right?
there are many boxes.
2.
No. There are, well,
I mean, hyperparameters, 3 boxes.
in the picture I have, there are 3 boxes.
Yeah,
Yeah.
with hyperparameters,
Yeah.
the third one.
Yeah. So let's see. So basically what you want to determine is what is the probability of, in a Bayesian world, you want to determine sort of posterior estimates of these parameters. You don't want to just determine a point estimate. That would be one thing you could do. But you also want to determine the distribution. So you want to determine distributions over the betas, the thetas, and the zij's, given the wij's, the etas, and the alphas. Okay? So this is a very gigantic probability distribution. You can break it down by the fact that we've generated this in a particular way. And then you have to insert the fact that these are coming from a Dirichlet. You can write down certain probabilities. These solutions are intractable. You can't really solve them. Essentially, you have to integrate out. If you do this in a Bayesian fashion, this is the joint distribution, which you can write down, divided by the integral over this. And that requires you to put in the Dirichlet parameters, and you can't estimate exactly. You need to approximate inference. And that's where you do things like MCMC methods or use variational methods, and again a bunch of other things that I will not cover here, but are a very interesting topic to sort of study if you're in the right class. Okay, so the goal here is compute. Yes.
You have to provide key.
Yes, for now. Yes.
Okay.
There's a way to get around this, but yes, for now you're providing. So this at least is, well, half of it, because the other half is the inference which I haven't told you. But this is the basic core idea is that you allow yourself to lift beyond fixed partitions into these Dirichlet distributions over partitions, and then posit a generative model in this particular form. So the very specific form. You can imagine other ways of doing it. This is one way, and that gives you this formulation, and it gives you all these parameters. And again, like I said, in full generality, you want to estimate the distribution of these parameters. You might ask for a single point estimate as well. If that's what you want. Questions?
Yeah, how do we do this?
That I'm not going to go.
That's spoiler.
Huh? Well, like I said, I mean the spoiler answer is that
I know it's not easy.
this is an integration that you cannot compute exactly, so you have to estimate it.
Yeah.
And there are MCMC methods. You basically use this thing called a collapsed Gibbs sampler.
Yeah, but I just want to know, like, I read a paper some time ago, but I forgot like most of it, how they did this and so on.
I don't think I'm competent to give you a full detailed explanation. So, like I said, you use some kind of Gibbs sampling, which is not surprising given there's an MCMC. That's one way of doing it. Or you basically do a variational method, which means you assume some independence properties and sort of you search over the space of products of these distributions. Or you use something. There are other ways of doing it.
Oh, okay, but what would be one way to do it? Like just see, like, the intuition, like how would you do it?
I wouldn't. I would take some standard code and do it. I would, but like I said, okay. So I mean, like I said, right? I mean, you can rewrite this as the entire joint distribution. Divided by the marginalized out version of this, which is basically a gigantic integration. This you can write down explicitly. This you cannot compute. This you have to estimate. So this is the standard problem. You have to estimate some kind of integral over a distribution. How do you do this? Use MCMC method. Again, this is something that, again, is A, beyond the scope of what I can cover in this class, and B, something I'm not even sure I know. So even if I try to explain, I'm not sure I'll do a good job.
Actually, this is pretty straightforward in almost all Bayesian estimation. Even
Yeah.
elementary Bayesian estimation.
It's a black box.
Yeah, you use Hamiltonian Monte Carlo, you use
Or-
variation of this.
Or Gibbs sample, yeah.
Yeah, there are like 300 such algorithms out there.
Which is why I'm being vague about this. Yeah, there's a black box, you have to run the black box and you do it.
Yeah, you can always treat this like as a black box.
No, but he's saying that's what you actually do.
It is an intractable problem unless
Yeah.
you have some kind of conjugates where you can come up with a tractable solution.
Right.
Most of the Bayesian estimation is like this.
I mean, think of it this way: you're basically doing counting.
Yeah,
And
that's
most
fine.
counting problems are hard, are sort of exponentially hard to solve, or at least we can believe they are. So you have to come up with some kind of approximation. So either the approximation by random sampling, which is an MCMC method, or the approximation by variational method, which is another kind of approximation.
Yeah, but yeah.
Think of it this way, okay? So to be more precise, right? I have some functional here, okay? And there's some distribution. I have to solve this problem. The way you have to solve this problem, if you can't do the integration explicitly, is by trying to sample from this distribution. Okay? Take a sample, evaluate f. Take a sample, evaluate f. Add them all up. Okay? So the problem of evaluating this integral reduces to sampling correctly from the distribution defined by the thing you're integrating with. Okay? As long as you can do that, there are results saying that, with the right estimates, you can estimate this integral. As long as f is reasonably well behaved, doesn't sort of jump around too much, you can do this. So you've now reduced the problem of doing the integration to the problem of doing sampling. And that gets you to MCMC. Because now I'm saying, how do I sample from this bizarre distribution? Well, I don't know how to sample directly from it, but I can build a Markov chain and do a random walk in the Markov chain, and eventually that random walk will converge to a true sample from the distribution. Now, how do I do a random walk? Well, there are Metropolis Hastings, there's Gibbs, there's collapsed Gibbs, there's whatever you want. Or if it's a continuous Markov chain, you have a Hamiltonian Monte Carlo sort of things. Wait, is it Hamiltonian Monte Carlo?
Hamiltonian Markov.
Hamiltonian Markov chains, the same MC. So yeah. So there are different ways you can go about doing this. Okay? But that's the idea. Convert the integration problem into a sampling problem, and then use some clever samplers to sample. That's about now you have now pushed me to the limits of what I can tell you without start making up crap. So.
I mean, we played a lot with these things.
Yeah, sure.
In class, probabilistic modeling.
Yes, and that's the right class to sort of learn about
Yeah,
this.
but thing is,
So there's a class that Tom Fletcher teaches, by the way.
yeah.
So.
So I like it. Yeah, we sample all those things, but there's like I'm missing what's going on behind, right? I want to understand, like, let's say with K, it's a much simpler model. With K-means, right?
Yeah.
You say you select points,
Yeah.
then those points move. Then those points move according to how you assign points
Sure.
to the clusters.
Sure.
Right? So what's going on here? I have these documents. I have these, the weights, and how do I know? How do those betas first of all betas moves, right? Somehow they get some assignment.
So here's the way. So the way to answer your question is this. If you go back to k-means, I think this is a good example. We have seen already that you can view k-means, the algorithm, as a particular consequence
Yeah.
of a generative model. So when we talked about the EM algorithm, what we said was, if you set up a mixture of Gaussians, and you at every step look at the max likelihood thing you can do, that max likelihood step turns out to be, oh, find the centroid by averaging. And the next step, the max likelihood thing turns out to be, oh, take the nearest neighbor. So the k-means algorithm is a byproduct of carefully inspecting the process of doing this max estimation and saying, oh, wait a second, there's a nice algorithm that pops out of this. We don't always get that lucky. This is the case we don't get that lucky. There are EM variants of how to solve this problem, and you could try an alternating method. But you don't always get that nice, clean, oh, here is the underlying algorithm coming out of it. Sometimes it's a lot murkier. And that's why you feel the sense of, I don't really know what's going on because I'm just doing some magic sampling and somehow I'm getting estimates. So I understand what you're feeling, but the fact that we get to the k-means is a lucky accident. And we should be grateful for that. You're not going to get that all the time.
Yeah, yeah.
And I think that's the best answer I can give to this. What's the real algorithm here? In a lot of Bayesian estimation, ultimately, you set up a problem and you compute some probabilities, right? Essentially, this is because what you're computing, remember, is not a single thing. You're computing a distribution over things. If you want to compute a single thing, like the map estimate, then it is entirely possible that if you look and say, okay, I want to find the thing here that maximizes this, then you push that maximization into here, you might be able to actually find something directly. And there might emerge an algorithm as a result of that. But again, it depends on the distributions you pick, it depends on the model. So as always, the more complicated your modeling gets, the harder the algorithm probably gets. Gaussians were easy in some sense. Right? I mean, I do believe that there should be something for LDA, kind of like mixture Gaussians, mainly because multinomials, in this sort of Bregman sense that maybe I've mentioned once before, are in the same family as Gaussians, they're just slightly different. Instead of reasoning with L2 squared, you have to reason with the KL divergence, and the thing should work. So there should be some kind of KL divergence version of k-means that will do the same thing for multinomials that you got for Gaussians. But I don't think it'll give you the Dirichlet stuff as well. It'll be, okay, we have a fixed set of multinomials, and you want to do this, and you can do it. This creates an extra twist. I think it's a nice question to ask. Is there some nice algorithmic consequence of this? But people have been looking at this for a long time.
Other than text classification, can it be used for other contexts also?
Well, I think LDA applies whenever you can posit a process that looks like this, right? If you could imagine, I don't think this would work very well, but you could imagine now that your words are pixels, your topics are colors. What you'd get from this, I don't know, right? You're basically saying any picture is a distribution over colors. And for a while, people used to use that as a way to describe images. You just take a histogram over colors and use that as a way to interpret what the document was about. So you could try this. I have not heard of LDA being that useful for images, but the notion of a topic model definitely could apply beyond text. Maybe, I don't know if it would apply well in sort of any generic sense. It seems hard to see why you would have a question in those sense.
We have large-scale purchase data,
Yeah.
gigabytes and gigabytes,
Ah.
of what people purchasing.
Okay.
It's always a question of how do we cluster these people. And there are many ways to cluster them, but this is an interesting way to look at. You purchase these type of things.
So
and these-
your person would be a document or a topic in this case, in this example?
A person. It would be a person.
So topic would be a person?
Topic would be a person, and we have a history of all the things that the person has behaved over time.
But if you have everything for a single person, that person must be like a document.
Yeah, exactly.
The topics
yeah,
might be
person
their
is
preferences,
Yeah,
or their
person
sort of
is like a
inclinations.
document.
So a person would be a document.
Yeah.
Their purchases are the words.
Words.
And the topics are their, I don't know, preferences, things,
yeah.
idiosyncrasies.
Yeah.
You could imagine trying this one. And in fact, it might even be better than document clustering because you don't necessarily need that sequentiality, or you don't need sentences to make sense. You don't need all this.
Yeah.
Have people try this?
Because not just purchases, we have their behavior, like how they bought under different
Sure.
situations.
So you could, yeah. So I mean, and then like I said, there are generalizations of LDA. I might talk about one of them in the time we have left, but there are generalizations of LDA that might be beneficial. For example, there are cases where you can think of these topics as being correlated in some way.
Right.
So you can define a slightly advanced version of LDA where now when you generate, you have extra parameters to describe the correlation between topics. And that's used when you generate topics for things. You don't just independently generate topics. There's some correlation parameters. So that might be of interest as well. So yeah, I think it's definitely something where you could at least try it. How well it would work, I don't have a good intuition for it. I'm not very familiar with topic models myself. But that's the whole point. This is very generic. You just have to replace these words in the right way and see that it makes sense. And then you should be able to apply it as well. And this is a black box. You can just run it and see. Yeah. Okay. Okay, I'll leave this up. Last thing I want to do in the time we have, and again, and we'll see how far I can get into it, is to talk about this whole, again, this annoying business of K. Because it turns out that once you go to this, so you could argue that we haven't really gained a lot from writing the Dirichlet world, except for the stability sample or multinomials. But it turns out one thing you can do, which is not obvious from this, is you can get rid of K. So something that was very hard for us to do in all our other clustering formulations turns out to be something that can be done here. Okay. And to do that, you have to go beyond a Dirichlet distribution to something called a Dirichlet process. And I think the word process there is kind of like the word programming, dynamic programming. It has nothing to do with what's actually going on. It just has historical relevance. That's why it's called process. So the idea of a Dirichlet process is to say, I want to generalize the notion of a Dirichlet distribution to an arbitrary number of clusters, to an infinite number of clusters. Right? And you can't just say, oh, we'll send K to infinity. These calculations and these probability evaluations don't always work. You have to come up with you sort of have to go through this backwards in some way. So what I would do is define the properties of what I want such a thing to satisfy. Okay? And then I will show you a way to actually construct such a distribution, how to sample from it. Okay. So, and this is a general construction. If you've ever seen things like Gaussian processes, you might have seen this thing before. But if you haven't, that's fine. I won't assume that you've seen that. Here's the idea. So I'm going to define, so what I want to do, so again, what is a Dirichlet distribution? Is a distribution over measures, over things in the sample. So my Dirichlet process is going to be a distribution over infinite dimensional distributions. Okay. So I have some things on the Dirichlet process. It has parameters alpha and G0. And the idea is that if I sample from this, some distribution G, this object should have the right properties that I want it to have. Okay. And so let me define what I want in this DP object in terms of what G should be. So the property that I want is the following. So assume you have some base distribution, okay, over the, see how to say this.
So, I have a few questions.
Yes.
So is G0 a distribution of a fixed size, or it can be infinite size?
It's a sum distribution over some measurable space.
Measurable size.
Yeah. It's a single distribution over some measurable space. Okay, so this is the property I want. So G0 is some distribution over some measurable space. Again, I have to be vague here because I'm not talking about a fixed dimensional space, some arbitrary space. Okay? So think of some measurable space here. Okay, there's some distribution over it. Now, here's the property I want. Let me construct an arbitrary, finite-sized partition of the space. So let me draw. So So this is going to be, I'm going to call this A0. I'm going to call this A1. I'm going to call this A2, A3, A4. This is some arbitrary, finite dimensional sized partition over space. Okay. Because G0 is a distribution over the space, for each such piece, there is a measure or a probability of the mass of that region. Because G0 gives a mass of 1 over the entire thing. Right? So it'll give a mass of something here, something here, something here, something here. So we'll write that as, so we'll say that this is G0 of A0 is the mass of this, G0 of A1 is the mass of that, and so on. Okay? So what I want is that if I sampled G from this black box that I haven't described to you yet, the property that it must satisfy, that G should be, is that G should be, G should look like a Dirichlet distribution, the finite dimensional one, with these parameters: alpha 0, G0, A0, alpha 0, G0, A1, alpha 0, G0. So in other words, what I'm trying to say is that I have this weird thingy over an infinite dimensional space. If I look at any finite lens over it, it should look Dirichlet. Because a Dirichlet distribution is defined as a finite object. It's a distribution over a finite. So for any finite subset, it should look like that. No matter what this partition is. That's what I want this DP to satisfy. Now, I don't know if such a thing even exists, but that's what I want it to look like. I want it to look like a Dirichlet distribution on any finite viewpoint. This is similar to how, when you define a Gaussian process, there's a Gaussian at every point. The property you want is if I take any fixed set of points, their joint distribution should be a regular Gaussian. So what I'm saying here is that if I take any fixed set of regions, the joint distribution on that should be a regular Dirichlet. That you get a Dirichlet process. Yes?
What is parameter alpha 0 unnecessary?
It's a concentration parameter. It's like why we need a concentration parameter in general. We need some concentration. Because see, remember, G0 is a distribution. So its total measure will be 1, right? You want me to scale things otherwise. So just like with the Dirichlet distribution, right? We said there were two parts to it. There was the concentration parameter, and there was which is the magnitude and the scale, and the vector and the point itself. These things give you the point, but to scale it and give you a concentration parameter, you need alpha 0. Otherwise, you won't be able to concentrate it anyway.
Okay, got it.
Yeah. Because these numbers are going to sum to 1.
Yeah, I understand.
So this is going to be the center of your distribution, essentially.
Yeah, it's just because of that.
Yeah. Okay.
So are these partitions are distributions or this measurable space?
They're subsets of the measurable space.
They're subsets.
Don't
Just the
think
subsets.
about them as distributed. They're subsets. There's some measurable space, there's some distribution, and there's some distribution of the measurable space.
So they are just the partitions.
Yeah. So just to blow your mind, G0 could itself be a Dirichlet distribution.
Yeah.
In that case, what I'm saying is that I have the simplex. I might have a finite dimensional simplex. And I'm saying, okay, let's break up simplex up into k pieces. And then I want this to happen there. So it gives you, so in some sense, it gives you much more power. You're going from just single points to arbitrary subsets of finite size. That's in some sense where the infinite dimensionality is coming from. You're reasoning over subsets instead of reasoning over entities. Okay, so I haven't really said anything yet because I have no idea whether this object even exists or not. There's no way. It's not clear to me how to even produce such an object. But the beautiful thing about this Dirichlet process is that you can actually write down explicitly. I can tell you how to write this down, and I can tell you how to sample from it. And that's the cool thing. And the thing that you use is this thing called, so first of all, through some fairly heavy machinery, it can be shown that this can be written as some kind of sum over pi I delta, again, phi of I, where I now goes from 1 to infinity. Okay, this takes some work, but it can be shown. In other words, the distribution has, I don't want to say finite support, but sort of countably infinite support. It's not a smooth thing. Right? Anything you sample from this is going to have a fixed discrete set of things at sort of specific points in the space, because it's a countable set. Okay? Then the question remains, what are these parameters and what are these things? It turns out these will be sampled from G0. So each of these is a uniform sample from G0. And these are the mixture coefficients. So you can think of a Dirichlet process, not surprisingly, as a mixture over an infinite number of things, where each thing is drawn, from one place. Okay. And how you get these parameters is by what is called a stick breaking method. So the problem now is I want to construct pi i's that get me what I need, and here's what I'm going to do. So in notation, so a Dirichlet distribution on two parameters is called a beta distribution. That's a special name for it. So what I'm going to do is the following. I'm going to sample pi 1 from a beta distribution on 1 and alpha 0. Remember, alpha 0 is a parameter there? Okay? So I'm going to draw a stick here. Let's say the stick is of unit length. So if I draw pi 1 from here, what's going to happen is that you can think of it as putting a dot in a particular location here. And this length is pi 1. Okay? And what's left is 1 minus pi 1. Now do this again. Draw pi 2. Well, let's draw beta 1. Beta 2, again drawn from beta 1 alpha 0. But interpret beta 2 as doing a stick breaking on, and do another dot here. So this becomes beta 2 times 1 minus beta 1. Okay. And so on. So you keep doing this. And so you get pi 1 is equal to beta 1, pi 2 is equal to beta 2 times 1 minus beta 1, pi 3 is equal to beta 3 times 1 minus beta 1 times 1 minus beta 2, and so on and so forth. And it's not hard to show that sigma pi I is going to be equal to 1. Almost showed you in the limit. It's infinite sum. So you can actually, and so you can construct these partition parameters in this manner. So you can actually explicitly write down what these numbers are. And the rest of it comes from that. So it is actually, in fact, possible to describe what this Dirichlet process is like. This is infinite mixture over distributions, where the mixture parameters are given in this way. Now remember when we went back to mixture of Gaussians, I said, oh, there's this mixture parameter. I can fix it or I can choose it randomly. Right? And I was going to choose from a Dirichlet distribution. Here what I'm doing is describing you a process to choose this infinite set of parameters randomly. So I can get a random distribution. So that describes the distribution over the space. Yeah.
So how do we get beta 2? I just wasn't sure. You sample, but then
Each beta I is drawn from a beta distribution.
Yeah, but why did you draw it there? You multiplied.
You multiply it. So you think of it this way. This is a sort of an imaginary process that helps you, well, at least tries to help you try to see
Yeah,
how
you want
this
to make sure it sums to.
Yeah, so you just sums to 1. So that will guarantee the sums to 1, the limit.
Oh,
You just-
and because it's infinite, you can actually do that.
Right, that's right.
Then you will get all possibilities.
Yeah, so this is called the stick breaking process. Because you're breaking the stick at every step. Take a stick, you break it. Take another, break it, break it,
Yes.
keep breaking it. And you can show this gives you a distribution uniformity.
Because if you were to do this for Dirichlet, you wouldn't get Dirichlet, right? We just said that last time. Because you get too small probabilities.
That was for uniform.
Yeah.
I'm not choosing uniform, I'm choosing a beta distribution. That's why this works.
Yeah, it's pretty cool.
So it's-
Yes, you had a question there?
is this for sampling from a Dirichlet distribution, or is this,
This is a way to describe. So, okay, let's bring it back up a second, right? The Dirichlet distribution, which was finite dimensional, was described by these deltas, which you chose from your base distribution there, and the mixture coefficients, which are a finite number. And I told you, oh, this is how you sample these coefficients, by using a Dirichlet distribution. For the Dirichlet process, which is infinite dimensional, I don't have a good way of sampling the pi i's. I can't sample from an infinite dimensional simplex, I do not do that. Alternately, I'm going to do that. So that's my replacement of the Dirichlet distribution sampling. That gets me this, which now gives me the infinite dimensional analog of a Dirichlet distribution. That make sense? Okay. So again, I have shown you how to construct an appropriate infinite sequence of numbers that form a partition, because the sum will go to 1. And you can prove that. That describe this infinite mixture. But that still doesn't tell me what an actual distribution from this family looks like. Remember, this is a distribution of distributions, right? And so this is merely saying, okay, this is how I randomly pick the pi i's. Okay, now you do that. You pick the pi i's. What does my actual thing look like as a result? And so the thing it looks like is this very cool thing called the Chinese restaurant process. And have you ever heard of a Chinese restaurant process? There are two. There's a Chinese restaurant process, there's an Indian buffet process. The Indian buffet process is a little bit more involved, for whatever reason. So, but this is a bit simpler. So, it's an unusual name, but it's kind of fun. It's a helpful way to think about it. So, okay. So again, what I want to tell you now is not, I have attempted to sort of describe what this distribution of distributions look like. And since it's a distribution over distribution, I want to sample from it and get a distribution. And I want that distribution to be an infinite dimensional partition in some sense. I want to have an arbitrary number of clusters in it. What does that thing look like? Okay, that actual sample. Here's what it looks like. So the only parameter I need is alpha 0, so I'm going to use it alpha 0. So imagine a restaurant, in this particular case a Chinese restaurant. I'm not sure why it had to be Chinese, but it is a restaurant. And it has many tables. It has in fact an infinite number of potential tables. Okay. So there's table 1, table 2, table 3, up to table infinity. Think of each table like a cluster. That's why you want to have an infinite number of tables. People are coming in. People are points. People are going to be seated at tables. That's the part of clustering process. Each table gets served a particular item on the menu, or a distribution of items. You've got to choose that distribution of items. If you don't like it, too bad for you. And so there's some distribution over food at each table. That's your individual cluster distribution. And people now have to be assigned to these. And so here's the game that gets played. So the first person comes in. There are no tables set up yet. The restaurant just opened. So they quickly set up a table, and the first person sits at the table. The first person sits there. Okay? That's my first cluster in some sense. Now the second person comes in. And the second person has a choice. They can either go sit with the first person at their table, or they can say, no, I don't like the food, I don't like the person, and start a new table.
So you know what's the food for the table?
No, this is an illustrative example. I mean, the food represents the individual, the distribution for that cluster.
Yeah,
like
I
say a
understand.
Gaussian or
But the
something.
person doesn't know the food at the table.
Person doesn't. There's no person knowing anything. There are points.
Yes, exactly.
It's a process. So think of it as a process. So the way the process works is that, you know, let me see how to write this out. So, yeah. Okay. So let's say n is now the nth person comes in. So n is equal to 2. Okay. With probability alpha 0 over 1 plus alpha 0, they go to a new table. And with probability 1 over 1 plus alpha 0, they go to an old table, in particular this table. Okay? So now second person is done. Maybe the second person decides to go to the same table as the first. So now let's say our picture looks like this. So I have one table and I have two tables. Okay? Now the third person comes in. Again, the third person has a choice of whether to go to a new table or not. But now, people are social. They don't want to go to the table all by themselves. If you've ever been to a conference, you know what I mean. So you would like to go to a table that there are people already there, so you can talk to them and all. So the probability changes. So now that n is equal to 3, the probability of going to an old table, a new table, again, is alpha 0 over 2 plus alpha 0. So in particular, n minus 1 plus alpha 0. So that's a new table. And the probability of going to this first table will be, n minus 1 over n minus 1 plus alpha 0. So let's say the person tosses the coin and says, no, we're going to go to a new table. So they come here. Okay, now we get n equal to 4. Now what happens? So our picture looks like this. I have two people here. I have one person here. Okay? So now we construct the denominator. It's going to be 3 plus alpha 0. That's the denominator here. The probability of going here is going to be 2 over 3 plus alpha 0. The probability of going here is going to be 1 over 3 plus alpha 0. And the probability of starting a new table is going to be alpha 0 over 3 plus alpha 0. All that. So that fourth person goes there. Keep running this process. The claim is that this process, at some point, you stop it at any given point, it has a distribution over clusters. Some number equal to the first one. That is a random sample from the Dirichlet process. Now, I'm not even going to start trying to prove this. These are a bunch of results that were proved, that were very powerful results that let us start using these things. But what this is telling us that there's an explicit sampling process that gives you a clustering that represents a random draw from that Dirichlet process. Notice here, you can always keep adding clusters. There's always a chance to add more clusters. As alpha 0 goes up, you have more of a chance of adding new clusters. So the number of clusters in the system is infinite, potentially. There is no bound. There's no k. So I want to cluster in this model, I never have to produce a k. The alpha 0 somehow controls how many k's I have. You can show that for this process, roughly speaking, the number of clusters will be like log n. That it grows roughly like log n. It's not hard to see. Basically, there's the chance that there's a fixed, small chance, a decreasing chance of getting a new point. If you think of this as alpha 0 as 1, then roughly the chance of creating a new cluster is something like 1 over n. So you integrate that, you get log n clusters. But that's important because now it's non-parametric. The number of clusters can grow and adapt with the data. Okay. And again, you can make this more involved. You can do more fancy things with this. There are different flavors of this. Again, the Indian buffet process is a different model for this. But the idea is that when you define this Dirichlet process, which is an infinite dimensional analog of the Dirichlet distribution, you get the power of having potentially infinitely many clusters, but a sort of a countable infinite number, so a discrete number. And you can generate a sample from the distribution by this process, and it has this nice explicit form. And this can be used to essentially learn clusterings for this more generalized version of it. Okay. So again, this last bit, I merely want to tell you to convince you that you can make these things fully non-parametric and get rid of k, and only keep the hyperparameters. You don't have to worry about the k parameter, but it gets more involved. And so you can take the regular LDA with Dirichlet distributions, and wherever you saw a Dirichlet distribution before, you replace it by a Dirichlet process. There's a bit more work you have to do, but that's the basic idea. And you get something called hierarchical LDA, and that gives you a truly non-parametric way of doing clustering. But that's the amount of work you have to do to get rid of k. All right. I have read probably about 15 different lecture notes on this topic, and they're all equally unsatisfactory. But I don't see any reason why I should suffer that pain myself. I'll give you the lecture notes, and you can also suffer the pain as well. But there is, I have not found, what I've told you today is probably the best I can come up with is a good sort of explanation of how these things all fit together. I've yet to find one that really satisfies me. So it's going to be interesting to try and write this all down in some way that makes sense. I'll provide some. There's some which are pretty good. Michael Jordan has some nice tutorials on this, and there's some other good lectures on this. All right, that's it. See you next week.